I'll be talking about ice tables in this video. Think of an ice table as a table that we put underneath a reaction. It allows us to quickly see and predict changes in the amount of something as a reaction goes on. The I represents the initial amount, the C represents the change in that amount, and the E represents the final amount. So we have a basic reaction here where our reactants A and B turn into our product C. We start with a certain amount of A and B. This allows us to produce C as time passes. But we don't keep producing C forever. Our reaction will eventually reach equilibrium. If you recall from my first video, the concentrations of our substances no longer change after we reach equilibrium, which is represented by the dotted line. As you can see, our products and reactants have constant concentrations after equilibrium. This means that we're going to end up with a fixed amount of A, B, and C at equilibrium. This equilibrium amount will be different than the amount we started with. Notice that A and B are at much lower values than they were when they started the reaction, and that C is at a much higher value at equilibrium than it is when we started the reaction. So what I was trying to show you with those graphs is that the equilibrium amount of something will be different than the initial amount of something due to some change that occurs. I'm going to introduce a basic scenario and problem and show you how to use an ice table to solve it. Pause and read over this problem. We're asked to find the K value, which is also known as the equilibrium constant. The first thing to do is to write down all our given information. We're given that our initial amount of A is 2.50 moles and that our initial amount of B is 1.50 moles. So we write that down on our ice table. We're also given that C is 0.75 moles at equilibrium, so I'll write that down as well. Now let me ask you, how much moles of C do we have initially? The answer would be 0.00 moles, because the exact moment we start this reaction, not enough time has passed to make any products yet. That is the assumption that we have to make when we are mixing reaction gases together and when there is no mention of any initial amount of product. So let's write that down. Alright, I'm going to go over the question again. It's asking for the K value, so let's write down the equation for that. Note that the K value uses concentrations of our substances at equilibrium. Since we only have the amount of C at equilibrium, we can't find it yet. We must find the amount of A and B at equilibrium. We haven't done anything yet regarding the change section, but we can find change if we have the initial and final amounts of something. Since we initially start off with 0.00 moles of C and end up with 0.75 moles, we can say that our change is plus 75 moles. That's great to know, but what can we even do with this information? The answer can be found by looking at the stoichiometry of this reaction. Everything in this reaction has a coefficient of 1. This means that we need 1 mole of both reactants to make 1 mole of products. In other words, 1 mole of A and B make 1 mole of C. Using that logic, if we made 0.75 moles of C, this would mean that we consumed 0.75 moles of both A and B. So we would say that the change for A and B is minus 0.75 moles. We then combine our initial values with the change to get our equilibrium amounts. So now we have all our equilibrium amounts. But there's one last step to do before we find K. We can't just plug these values into the expression because it's asking for concentration and we have moles. In order to find concentration, we must divide moles by liters. Luckily, we are given that this reaction takes place in a 2-liter container, so we would have to divide all our equilibrium amounts by 2 in order to get our equilibrium concentrations. Once we do that, we can finally solve for K, which is around 1, but it is closer to 1.14 if you ignore sig figs. So I hope that you could follow along. Ice table problems will look something like that. You'll be given a few variables and asked to solve for something else using that information. I'm going to do another ice table problem, but this time it will be different. We're going to integrate the reaction quotient into this problem, and we're going to deal with coefficients bigger than 1. Let's start. Pause and read the problem. So this problem is different than our previous one. This time, we're being given our equilibrium constant and being asked to find the equilibrium amount. Let's start by writing an icebox with our given reaction. Our problem says initially have 1.5 moles of A and 2.5 moles of B. It's implied that we have 0.0 moles of C for the same reason as stated in the previous problem. I wrote that all down. Now the next step is to find a reaction quotient. The reason so is because we want to compare Q to K and see which way this reaction will shift. I'll put down the expression for Q. Now remember, Q uses concentrations that aren't at equilibrium. This means that we can put in all our initial values instead of our equilibrium values. Let's do that. Now we can quickly see that there's going to be a 0 in the numerator, and from that we can quickly conclude that Q is going to be equal to 0. When we compare this to K, Q is less than K, and if Q is less than K, the reaction will shift forward. This is important because we know we're going to lose reactants and produce products. It's always important to watch out for this because there are times when it's the other way around. As a general rule of thumb, if you start with no products, your reaction will move forward. But if you do start with products, make sure to find Q first. So let's recap. We know the reaction moves forward because Q is less than K. So we know that we're going to consume reactants and produce products. The issue is that we don't know how much reactants we consume or how much products we produce. But if we take a look at the coefficients of the reaction, we can see that 1 mole of A and B will produce 2 moles of C. So no matter what, the amount of C we produce will always be double the amount of A and B we consume. We represent this unknown amount that we consume with the variable x. If this reaction proceeds forward, we lose a certain amount of A and B. That amount that we lose will be the same for both of them because they share the same coefficient. So we would say that the change is minus x for A and B. On the other hand, the change would be double for C because of its coefficient of 2. It also would be added because the reaction is moving forward and we're going to be making products. So we would say that the change for C is plus 2x. We can then write down our equilibrium amounts as expressions instead of actual numbers. They're not exact numbers, but don't worry about that, we're getting there. The problem gave us the value for K, and we can finally use that number. We're able to write down the equation for our equilibrium constant since we have our equilibrium expressions. What we're trying to do is that we're trying to solve for x and plug that value into the expression for the equilibrium amount of C. That way we can find our answer. If you have a calculator, you might be able to use the solve operation to find x. But if this question were an AP exam multiple choice question, you would be expected to use a shortcut due to time constraint and because of the no calculator policy. So I'll teach you about that shortcut. It's based off a conceptual application of the equilibrium constant. Look at our equilibrium constant. It's a very small number. According to this equation, a very small number means that we're going to have a small numerator and a big denominator. So this means that we're going to produce a very small amount of products and that we're going to consume a very small amount of reactants. We could even say that the amount of reactants we consume is negligible. That means we basically don't consider the loss of reactants since we lose such a small amount. In other words, 1.5 minus x is just basically 1.5, and 2.5 minus x is just basically 2.5. So let's apply that onto our equation. By doing this, it becomes so much easier to solve for x. We removed x from the denominator and we don't have to worry about that anymore. The process for solving x becomes much more straightforward. Once we clear up the equation, we get that x is equal to 0.00020. This confirms what I said earlier, that the amount of reactants consumed is a negligible amount. Now that we have x, we can simply put it into the expression for the equilibrium amount of C. We get 0.00040 moles of C at equilibrium, which is our answer. But some of you may be thinking, what if my K value isn't small? What if I can't assume that x is negligible? A situation like this, for example, can be difficult to solve for x. You need a graphing calculator. In this instance, K is pretty large, so we can't just neglect the change in x. So to solve for x, we would first need to graph the K value by itself. So set y equals to the K value. In this case, I would set y equal to 35. You should see a horizontal line. After that, graph the other expression right here. You may have to zoom in, but you're looking for when these two graphs intersect each other. The x value for the point at where the graphs intersect each other will be the answer. If you see an intersection point where x is negative, then you must ignore that. Only look for a positive x value. So in this case, x is equal to 0.566. After that, you just continue as normal. You probably won't see this type of question in a multiple choice, but it might appear in an FRQ. You're going to be required to do this for one of the upcoming practice problems. So with that earlier problem, I introduced the concept of checking the reaction quotient, unequal coefficient ratios, and the idea of ignoring x if k is a small number. I'm going to put a practice problem for you. Pause and take some time to answer this question. Good luck. So the first step I did was that I wrote down all my given information on an ice table. I know I'm going to have to solve for the equilibrium amounts for nitrogen and hydrogen because the question is asking me to find K. After that, I take a look at the stoichiometry of the reaction. 1 mole of nitrogen and 3 moles of hydrogen produce 2 moles of ammonium. This is quite an uneven ratio, but we can still work with it. Since we end up with more ammonium than we started with, we know that the change is going to be plus. It's going to be plus 2x because of the coefficient on ammonium. On the other hand, if we're increasing the amount of ammonium we have, that means we must be consuming the amount of nitrogen and hydrogen we have. So we're going to have to minus a certain amount for change. It would be minus x for nitrogen and minus 3x for hydrogen due to their coefficients. Now, if I start with 4.0 moles of ammonium and I increase by 2x to end up with 5.0 moles, then I can do some simple algebra to find out that x is equal to 0.5. Once we figure that out, we can plug that in to find our equilibrium amounts of nitrogen and hydrogen. We end up with 2.0 moles of hydrogen and 5.0 moles of nitrogen. Now that we have all our numbers, we can plug it into the equilibrium constant equation and end up with a value of 1.4. I hope you got the right answer. Alright, here's another practice problem. Make sure you have a graphing calculator available. Also, make sure you pay attention to the fact it's asking for pressure and not concentration. So don't be afraid of the different units, you're still going to follow a similar process. I also will warn you that there's a red herring in this problem. Good luck. Alright, the first thing to do is to find Q so we know which way a reaction will shift. So we write down our expression for Q and we fill in all our initial pressures. Now you may be wondering, why don't we divide by 8 liters like we did with the other problems? The reason is that we needed to find concentration for the other problems, and that required us to divide moles by liters. In this case, we only need to find pressure, and that's already given to us in the form of atmospheric pressure. So there's no need to divide by 8 liters. That's why it's a little bit important to pay extra attention to partial pressure problems, since they may try to throw you off with unnecessary information. After that, we solve for Q and find out that it's less than K. That means our reaction will shift backwards. Okay, now let's start on our ice table. First, I write down all my given information. As stated before, our reaction is moving backwards. So this is different than what we saw before. Instead of gaining products, we are losing products. And instead of losing reactants, we are gaining reactants. I represent this change through x, as we have usually done. This time, it's minus x on the product side and plus x on the reactant side. After that, we have our equilibrium pressures as expressions. Now our answer requires us to find x to get the exact number instead of leaving it as an expression. To solve for x, put all our expressions into the equilibrium constant equation. Now this time, you can say that the change in x is negligible because k is a rather large number. So you have to use that graphing technique I showed you earlier. After doing that, I end up with x is equal to 0.022. Now that we have x, we can just plug it into our expressions and get our 3 answers. So there you have it. I would admit that I forgot to put my units in, but it's the same units that we started off with. Well, we're finally done. That felt like a long ride for me, but hopefully you understand how to solve ice table problems now. Anyways, thanks for sticking with me. Goodbye.